welcome back. Welcome to a quick live video. If you've been following the conversation about the Math64 library, which is a few weeks ago, I had to do a secondary video which took a lot longer. Just refresh your memory for a second. It's in the beginners section of the forum. It's a 64-bit floating point library. Now, what I started to think about the other day was I wonder if we could do particles with this kind of approach. We could have the bulk of the work being done by the Math64 library, and then we just plot the points out using just normal PB code. But before I did that, before I started with that, I needed to write an example to port something. So here's the example I put together the other day. Straightforward. We just got very basic gravity. Particles are moving out in all directions, like an irregular explosion. We'll just run that for you. Right, so we put our mouse in the middle. We're talking about 80 odd thousand particles, and we're getting about 700, 650 estimated particles per second. And our frame rate drops down to about 7 or 8 frames per second. I'll just get out of that, go back to the top of the board there as well. Now that's all well and good, but I thought about the approach I'm using here is quite straightforward. So I thought, well, what if I try and rearrange this code so it performs a bit better? By straightforward, I mean I've created a structure, a type in PB. I made a one-dimensional array with enough slots for all the particles. And we are just spawning particles every frame between 1 and 2000 and then drawing them. So we're getting a real choked level of performance. There's a number of things in this program that are simple but are they're hindering our performance as we go along. So this is the first version. We just go through the code there, our spawning operation. We'll have a look at that function. Pretty similar. We've got to count the location that we want to spawn the particle from. So if we're just running through and doing this addition operation a bunch of times, we're looking for a cell that's empty within the array. Once we've got one, we allocate a structure for it, get a pointer to this structure, and then fill out the fields. We record its location, compute an angle, give it a speed, and then give it a vector for its x and y movement. So we're not using polar coordinates when we're actually updating them, but we are initially. Just it's nice and easy. The draw function is pretty much what you'd expect. We're running through the entire array, checking does the particle at this location exist? If it does, getting a pointer to it. Then we start doing the work on the particle. We start adding its velocity to its current x position. Do a range check. If it's outside the range, we kill it and continue on with a loop. If it's legal, we step through. We're adding our y velocity. And we're checking to see whether we're inside the viewport again. I'm just using the default 800 by 600 viewport. I've hard-coded the values in here, which is a bit of a no-no, but I've done that for just the sake of a demo. So here we're making sure the particle is inside the screen because we're going to use fastdot to plot it. Fastdot has no clipping. So we're assuming that the only particles that are outside of the viewport are very few. And when they're outside of the X viewport, they'll be clipped away anyway. But vertically, we need the particle to be able to fly up into the air and then gravity to pull it down. And this can occur back on screen. If it leaves the bounds of the X screen limits, it's deleted anyway. So once we've drawn the thing, we apply some simple gravity to it and record its current location. So the process is very simple. So I thought this might be nice for something to do with Math64, but we need a bit more complexity in our Math64 to handle this kind of thing at the moment. But we can make this version perform better. This is the basic version. Don't know why I'm saving it, but I'll just save it again. That's example 1. Now example 2, I've tried to eliminate the allocation. I'll see how it performs first of all. I think it performs about the same actually. We've got a very marginal improvement where we'll say about 8 frames per second. So we've got about 600 and maybe 700,000 particles per frame. because the frame rate's going to jump up and down a lot. And all I've done for this particular version is I took out the allocation. So when we add new particles, because we're adding a lot of these particles every frame, 1,000 allocations that would work out to be. So what I thought, well, if I allocate over 100,000 particle structures up front, and I just recycle them as the frame goes, every frame, rather than allocating them. So we've got a thing called particle bucket here. We've got to fill it up full of these types. I've got 500,000 actually. So I've got way more than I need. I made an array. This is I redeemed our bucket array, which is global. I've allocated a structure and put the handle of that type in this bucket. I can't delete it from here, from the bucket, and the reason for that, if I do that, this handle I've just recorded is now invalid. So I have to use a bit of a hack here to reset this array, which is done here. I grab a pointer to it and I clear this memory directly, which is the same as undimming it, but we're not freeing all the types that were in it. So I've got the handles to a bunch of types that PB allocated for us, but I've sort of done it covertly. I put the number in the bucket at cell 0, and we just use that when we need one. So the only thing that's different is spawning and deleting. When we spawn something, we grab the top handle, particle handle from the bucket, place it in our array. If this is the exact same thing as going this new particle, or whatever the type was called now, I'm not sure. And then we're altering our index for the particle bucket down to the one below it. That does away with the allocation. When we free these things, we have to put them back in the bucket. So there's a bit of messing around to do this. So our draw loop, when we delete something, we're adding the index that needs to be freed to a temp array, keeping a count of how many that we've been deleted this frame. At the bottom here, we've got a bit of code that runs through and does this job for us. It's kind of confusing because we're using sort of mishmashy terms. I just threw it together, quite literally just threw it together. I've got a pointer to a type that emulates a normal PB array, kind of, in a sort of way. So I'm going to get a pointer to our particle structure here. We process all the ones that need to be deleted. We'll grab its index, which is the one where we recorded where it was being drawn and it needed to be killed. And we copy this particular this handle, what's going to be back onto the bucket which is what this does here. And then we need to clear this. If I try and use particles index equals 0 or null, that would undim that type, and we want to reuse it at some other point. So I've got to use that hack again to get rid of it. It's not really a hack, but it's an alternative way of doing the same thing. So that's example 2. We still have structures in there though. Another way you can do it is just having basically the same principle, but there's less work in it actually. So this version just uses a big block of memory and as a bucket. So all the particles just sit in this big block of memory, and we just have our particle bucket is just a list of pointers to those things. Give it a run anyway, see how we go. So we're creeping up there in terms of performance. We're getting rid of some of the issues we're having before. So we're now starting to get to 9-10 frames per second. It's going to vary all the time because it's random as we're going through. So for a real test, we probably should have very strict conditions on where the origin point is and the number of particles being added every frame. So we can repeat this test with different versions of the routine and go, that's the quickest version. Let's check it out. Good. Right. So we're doing a lot of work, but we're not really quite fast enough there for it to be an impressive effect at the moment. As I was just saying, we've got our particles. This time we don't have a typed array, we just have a normal integer array. And I'm going to store pointers inside that to particles. I've got a particle bucket again, but I'm not storing a handle of a type, I'm storing a pointer to the type in memory. I'm doing away with the handles altogether. I'm just emulating what that same process does. When we create the bucket, we just allocate a big chunk of memory in a bank, the size of our particle, and so if this is how many bytes, 32 bytes or wherever it is, I have no idea. It's just 32 bytes multiplied by this, so we end up with a big chunk of memory that we're going to pretend like it's an array. We're going to treat it like it's an array, I should say. Here I'm just allocating a bucket. We're looping through from the particle 1 through to max, getting our pointer to this bank that we just allocated, getting the size of this particle and multiplying it by loop. So initially, all of the pointers are effectively starting at particle 1, and then it'll be particle 2, 3, 4, 5, and they'll be all consecutive in memory. They're not spread around in memory at all, they're just one big blob of memory. We're just recording the pointers to where these things are in memory. Here, just putting the number of particles in our buckets. So the drawing and the allocation are the same. There's not much difference. We've got rid of this is an integer array now, where it used to be a typed array, but the code's basically doing the same thing. We're grabbing a pointer off our bucket heap into here, grabbing this pointer and filling out our structure. All the same basic stuff as before. Our drawing has got a little bit simpler. We're checking to see if this particular cell in our particle array is empty or used. If it's 0, it's empty. If it's anything else, it's a pointer to a particle. We put that into a typed pointer here. Me is declared as T particle pointer. Now we can use me as if it was a just normal typed array or typed cell or whatever you want to call them. The code here is the same. The killing mechanism is slightly different, but not much really. Where when we release this particle, we put its pointer back onto the top of the bucket, and we clear this particular cell in our particles, and we just continue on. There's no cleanup, no nothing. We don't need any of that stuff in this version. So that all works pretty good, but we still have some memory, some thrashing going on. If you look at the spawning method down here, when we spawn something, we're calling this get free cells. Now, because we're doing thousands of these calls, and this array is getting bigger and bigger and bigger, this particles array, it's 100,000 cells in size, or probably more than that. I'm not paying any attention to how big it actually is. I'm just going, well, let's let it get bigger, who cares? So it's possible that you might have to search through 100,000 active particles to find a free slot. So it's obviously a bottleneck there. So what our version 4 does is, you've already guessed it by now, we just pull that logic out. We have now a free particle list down here, and this is allocated to the same size as these particles. So this stores what indexes of particles have not yet been used. It's just a heap. We just put anything that's free goes onto the top of the heap. They just stack up, and then we pull them off when we reuse them. Our sporting becomes the same, almost the same as before. Rather than use get free cells, we just grab from the top of our free particles heap and then just decrement the heap index down. Make sure we get a pointer to structure for this particle, and then we just continue on. Nothing's all that different. Performance wise, it works much better. Now we've got rid of all of that sort of baggage from it. So we're capturing the screen here. We've lost a bit of the get up and go about the routine, but as you can see, we've probably doubled the performance of the application, and it's actually manipulating every particle there by itself in the runtime. Without capturing it, runs about 30 frames per second, but you know, things happen. You might have seen other demos that do this on the forums, but they use shapes. That's a much easier approach to get this level of particles, by the way. But for now, this is kind of where we're at with this. We'll try and see if we can update the math library to help us with this kind of job. If we can make the math library, we can outsource some heavy processing, number crunching stuff to the secondary library. It does a very tight and very concise job of what it's doing, and we can just render the points ourselves. Hopefully that would work out to be quicker again. Don't know. We'll find out, I guess. Anyway, thanks for watching, and I'll put the code in the board as per usual, and you're welcome to play with it. If you can make it faster, good on you. These methods here are pretty simple and have been used in a bunch of other examples on the boards over the past 15-20 years. So there's nothing new, but I'm just hoping to use this as a testing ground for our math library. Until next time, have fun, and I'll see you later. Bye.